Welcome back, everyone. In the last video, I introduced you to the definite integral, and this represents the exact area under the graph of a function on a particular interval. And the way that this is defined is with that limit you see there. We added up the area of a bunch of rectangles and let the number of rectangles approach infinity. But actually going through with that limit is not exactly a pleasant experience. And in this video, as well as the next few videos, we're going to talk about ways that we can compute definite integrals without having to compute this limit. As an example, let's say we want to compute the integral from 1 to 3 of x minus 1 dx. And as a reminder, the dx there is not actually part of the function, and it's not what you're actually integrating, it's more so just telling you what the independent variable is. It's very easy to forget to include that dx when you're writing these integrals, but it is an essential bit of notation that you do need to include with every integral. But back to the computation at hand. Computing this definite integral is equivalent to finding the area under the graph of y equals x minus 1 on the interval from 1 to 3. And oftentimes that area is not easy to compute, as we saw in the last couple of videos, if that area is not a familiar shape. But let's graph this function and see what we get. And y equals x minus 1 is a linear function, so it's not too hard to graph. And you can see that line in red, and what I shaded in blue is the area under this curve from 1 to 3, because 1 and 3 are the limits of integration. And we can see this area is actually a familiar shape. This is a triangle, and hopefully we all know how to find the area of a triangle. The area is 1/2 the base times the height. And in this picture, the base of the triangle is 2, and the height of the triangle is 2, and 1/2 of 2 times 2 is 2. And so the area of that triangle is 2. And what that means is that the definite integral from 1 to 3 of x minus 1 dx is equal to 2. And so we're able to compute our very first integral by being able to compute the area of this triangle. Let's do another example, and let's compute the integral from 0 to 3 of x minus 1 dx. This almost looks like the same as the previous example, but notice that the lower bound is a different number. The lower bound is not 1, but 0. And let's see how this would affect the answer by once again looking at this on a graph. And this here is the same function as before. It's still y equals x minus 1, so the line is still the same. But now the shaded region is not from 1 to 3, but from 0 to 3. And notice that the function goes below the x-axis from 0 to 1, and that's why I had to shade below the x-axis. The area is always the area between the x-axis and the function. And we already know the area of the triangle on the right. That has an area of 2. And what's the area of this smaller triangle? Well, the base is 1, the height is 1, and so the area is 1/2 of 1 times 1, which is 1/2. But since this function is negative from 0 to 1, we have to treat this area as though it's a negative area and subtract it from the area of the triangle on the right. And so the answer to this definite integral is 2 minus 1/2, which is 3/2. So keep that in mind that any area below the x-axis counts as negative area, and you need to subtract it away. Next, let's compute the integral from 0 to 1 of the square root of 1 minus x squared dx. And the question here is still the same. What is the area under the graph of y equals square root of 1 minus x squared on the interval from 0 to 1? But as you're looking at that function, you might not know exactly what that looks like. But let me rewrite it a little bit. Let's take y equals the square root of 1 minus x squared, and let's square both sides of that equation. And so we'll get y squared is equal to 1 minus x squared. And then if I move that x squared over to the other side, we get x squared plus y squared is equal to 1. And this is the equation for a circle with radius 1 centered at the origin. And so going back to the original equation, the function y equals the square root of 1 minus x squared is the top half of x squared plus y squared is equal to 1. So this is a semicircle. And the reason it's only the top half is because when I take the square root, I'm only getting the positive outputs. And so this is all of the positive y values, so it's everything above the x-axis. So we get that nice semicircle. And looking at the graph, we can see this is the top half of a circle with radius 1. And I shaded only the right side because we are taking the integral from 0 to 1, and that 0 and 1 always represent x values, because that's my independent variable. And so I need to find the area that I shaded there in blue. And that might not be immediately familiar, but keep in mind that this is part of a circle. And the area of the entire circle would be pi r squared, and since r is 1, that would be pi times 1 squared. But this is not the entire circle that we're looking for. This is 1/4 of the circle. So let's take the area of the entire circle, which would be pi times 1 squared, and divide that by 4 to represent this shaded region, which is 1/4 of the circle. And so the answer to the integral from 0 to 1 of the square root of 1 minus x squared dx is equal to pi over 4. But this did take a little bit of algebra before we even got to this point, just to realize that we actually did have a semicircle. And finally, let's end by computing the integral from 0 to 2 pi of sine of x dx. And this is the area under the graph of sine of x from 0 to 2 pi. And hopefully the graph of sine is familiar to you at this point. And if you draw that and shade in the region from 0 to 2 pi, we get this shaded region here in blue. And looking at these shapes, these are not circles or triangles or rectangles. I do not know how to find the area of either of these shapes here. But what I do recognize is that the area of both of these shapes is exactly the same. And so if I take the area above the x-axis and subtract away the area below the x-axis, that's going to be exactly 0 because they are the same. And so without actually computing the area of either of these shapes, I know that the integral from 0 to 2 pi of sine of x dx is equal to 0. Now most of the integrals that you compute will not be as simple as just drawing the graph, shading in the region, and adding up the areas. And we're going to get to some other techniques in the next few videos, but these kinds of problems build a lot of intuition for what you're actually finding when you compute a definite integral.